Okay, let's jump right into this explainer and explore what has to be one of the absolutely most mind-bending mysteries in modern astrophysics. Seriously, we're going on a journey today that challenges pretty much everything we thought we knew about the universe, time, and the very fabric of space itself. So buckle up. I want you to try and picture this. Imagine a pitch-black abyss where billions of dark particles are currently sparking explosions. Explosions massive enough to create entirely new universes. An abyss where there is literally no light, no visible stars, no planets, zero galaxies. Everything has just been swallowed up. Yet inside this total, complete darkness, microscopic particles are setting off chain reactions, potentially birthing distinct universes, each with its own physical rules and its very own flow of time. Now, you might be wondering, how could we possibly know this? Well, to understand the present and the future of black holes, we actually have to take a step back and look at how we discovered them in the first place. Remember when that famous photograph was released back in 2019? The whole world celebrated it as the first ever actual picture of a black hole. It was everywhere. But honestly, the scariest part of what we captured isn't that glowing ring of fire on the outside. It's the absolute pitch black darkness right in the middle. Because that is the place where no light, no telescope, and no signal can ever reach. It's a place where the foundational laws of our physics seem to just completely break down. But, the scientific community wasn't exactly eager to embrace a place where physics just stops working. Let's trace this back a bit. Picture this. It's 1930, and a 19-year-old Indian scientist named Subramanianan Chandrasekhar is on a ship, traveling from India to England. He's got weeks to kill on the ocean, so what does he do? He sits on the deck and calculates a mathematical equation combining the physics of dying stars with Einstein's relativity. And he discovers that a heavy enough star must inevitably collapse in on itself. But flash forward to 1935, when he presented this idea to the Royal Astronomical Society in London, Sir Arthur Eddington, who is basically the most powerful astrophysicist in the world at the time, publicly mocked him. He literally said nature would never allow such a bizarre collapse. Chandrasekhar was humiliated. He actually left the field for America. But here's the kicker. 48 years later, he won the Nobel Prize for this exact equation, proving that black holes absolutely must exist. So to understand how this terrifying darkness actually forms, we have to talk about how a star dies. You can think of every star as being locked in this lifelong, billions of years war between two massive forces. On one side, you have gravity, constantly trying to crush the star inward. On the flip side, you have nuclear fusion at the star's core, which is hydrogen atoms violently fusing into helium, pushing immense explosive energy outward. This delicate little tug of war keeps the star stable for a very long time. But eventually, the hydrogen fuel runs out, the fusion stops, and in a split second, that outward push just disappears, and gravity violently crushes the core inward. And Chandrasekhar actually did the math on this, and proved there is a precise tipping point. He showed that if a dying star's core is greater than 1.4 times the mass of our sun, the sheer, unimaginable force of gravity completely overpowers the internal pressure of electrons trying to repel each other. At that point, the star has absolutely no choice but to collapse. Today, we famously call this 1.4x barrier the Chandrasekhar limit. Which brings us to what you probably learned in school. The traditional explanation is that the star just keeps collapsing until it forms a singularity. A singularity is defined as a theoretical point at the center of a black hole where a star shrinks to absolute zero size and its density becomes infinite. But I'll let you in on a little secret. Many of the world's top physicists actually hate this idea. They completely reject the concept that a true singularity exists in reality. Why? Well, because in physics, getting an answer of infinity is usually proof that you've made an error. Think of it like a Google Maps glitch. If you're driving at night and your GPS screen suddenly goes totally blank, it doesn't mean the Earth has ended and you're about to fall off the edge of the world, right? It just means the map hasn't been drawn for that specific area yet. In physics, a singularity is exactly like that. It's simply a warning sign that our current mathematical and theoretical models just lack the capability to understand what is actually happening at that extreme scale. And this infinity error has been haunting scientists for literally centuries. Way back in 1783, an English scientist named Jean Michel first theorized a dark star whose gravity was so strong that even light couldn't escape. Then, incredibly, and this is wild, in 1916, a German soldier named Karl Schwarzschild was sitting in a muddy trench during World War I, surrounded by literal explosions, solving Einstein's newly published equations by hand. He was the first person to find an exact solution for a black hole. But his math hit a wall where the numbers just turned into infinity. He knew it was an error, a missing piece of the puzzle. But tragically, he died of illness before he could ever fix it. So the crucial takeaway here is that scientists knew nature hates rule breaking. In fact, nature tries twice to stop a black hole using quantum rules. First, it tries to create a white dwarf, where quantum mechanics forbids electrons from sharing the same state, creating a pressure that fights gravity. Now, if the star is too heavy for that, the electrons are shoved right into the protons to become neutrons, creating a neutron star. This is an object roughly the size of a city, but it's so incredibly dense that a single spoonful weighs millions of tons. Wrap your head around that. But if the core is roughly 2 to 3 times the mass of our sun, even that mighty neutron pusher fails. Gravity wins the tug-of-war completely. And this poses a massive, glaring question. If all physical limits fail, what stops a singularity from forming? If the star's internal forces and quantum rules can't stop the collapse, what is stopping the core from shrinking into an infinite zero? For a really long time, we just had no answer. But in 2014, 2 physicists, Carlo Rovelli and Francesca Vidotto, looked at a radical new model to solve this exact problem. Their solution stems from a groundbreaking theoretical framework known as loop quantum gravity, or LQG for short. The core idea here is absolutely fascinating. It says that space is not this smooth, continuous, infinite void. Instead, space itself is quantized. It's made up of tiny, indivisible, individual blocks, almost like digital pixels. Just like you can only zoom into a smartphone photo so far until you just see individual square pixels, space itself has a fundamental underlying structure that literally cannot be divided any further. And this absolute minimum pixel of space has a specific size. It's known as the Planck length, which is 1.6 times 10 to the power of negative 35 meters. This is it. This is the absolute minimum limit of space in our entire universe. Space simply does not exist at a scale smaller than this number. To really wrap our minds around how small that is, because it's hard to visualize a number with 35 zeros, consider this staggering analogy. If you enlarged a single atom to be the size of the entire Earth, the Planck length would still be smaller than a tiny speck of dust. It is phenomenally, unimaginably microscopic. But crucially, it is not zero. So what happens when a collapsing star hits this pixel limit? Well, it reaches what's called the Planck density, which is a mind-boggling 10 to the 96th power kilograms per cubic meter. The researchers realize that, just like a balloon pops when it reaches a certain pressure threshold, the very fabric of space pushes back when matter is compressed to this exact density. Basically, space flat out refuses to let matter shrink any smaller than the fundamental pixels of reality. So instead of forming a singularity, boom, the collapsing star hits a quantum floor. It stops shrinking entirely and forms what they call a Planck star. This is a tiny, impossibly dense, collapsed core that has reached the absolute pixel limit of the universe. Because space itself fiercely repels the matter at this scale, the collapse is abruptly halted. And here, my friends, is where loop quantum gravity introduces the ultimate twist. When that star hits the bottom, it doesn't just sit there. The immense pushback from space causes the Planck star to instantly rebound. It violently explodes outward. And the math suggests this isn't just your standard explosion, it's literally a Big Bang. The theory proposes that our own Big Bang wasn't a sudden beginning from nothing, but a bounce from a previously collapsed universe. And even more astonishingly, a new Big Bang is currently happening inside every single black hole right now, creating a brand new universe with its own unique flow of time, hidden safely behind the event horizon. But hold on just a second. I know what you're thinking, because this brings up a very logical follow-up question. If a massive Big Bang explosion is happening inside black holes right now, birthing new universes, why don't we see it? Why is the center of the black hole in that famous photo so pitch black, as if nothing is happening at all? The answer lies in Einstein's theory of relativity and time dilation. See, time flows differently depending on the mass and gravity of your environment. Inside the Planck star, in its own local time, this explosive bounce happens instantly. It lasts only a fraction of a second. But for us, standing way on the outside of the black hole's immense gravitational pull, time is drastically distorted. For an outside observer, that split-second explosion is stretched out over billions, even trillions of years. It is quite literally playing out in ultra slow motion. As the source material beautifully puts it, we are essentially looking at a frozen Big Bang, a cosmic explosion paused in time. Current estimates suggest that the light and energy from these exploding Planck stars will only finally breach the event horizon when our own universe is incredibly old, when most of our stars have died out and the cosmos has gone dark. Now, to be totally fair, we must impartially note that loop quantum gravity and Planck stars are still theoretical models. They haven't been definitively proven yet. But hey, as we saw with the young Chandrasekhar back in 1935, nature has a funny habit of proving early skeptics wrong. Sometimes, the math sees the truth long before our telescopes ever do. So, I'll leave you with this. The next time you see a photograph of a black hole with that glowing ring of fire around the pitch-black abyss, ask yourself, will you ever look at it the same way again? Knowing that behind that darkness might not be a destructive end of infinite nothingness, but rather a frozen moment of creation? Entire new universes suspended right there in the dark, just waiting for the clock to catch up. Thank you so much for joining me on this explainer, and keep questioning the universe.